Thanks again for joining me on these videos looking at how global climate change from the globe down to the Outer Hebrides and how we understand climate change. And a very common question within climate science is how do we know the climate's changed, or do we know that the climate's changed before? And the answer is that of course we do. And we've been studying past climates for decades, and our records go back actually quite detailed, back as far as 65 million years. So I've taken this figure from this paper by Westerhold et al. Back in 2020, and I quite like it. It sort of gives a wonderful outline of our climate. So far left here, we've got about 65, 70 million years ago, and the upside down dinosaur, just to indicate that they've died at this point. And at that period, we left the Cretaceous period, and we entered into sort of the most recent set of epochs, the Paleocene being the first, and we worked through the Eocene, the Oligocene, the Miocene, the Pliocene, the Pleistocene, which obviously everyone famously knows as being the Ice Ages, and then the Holocene, the most recent period, with the rise of man and woman, up until the occurrence of the Anthropocene, which is where we sort of have been. It's been said that we are now living, and what you can see in the shading in the background is actually how the world was considered to be, whether it's hot or warm or cool, or then an ice. And you could see that the climate has significantly changed, and that the climate of sort of 50 million years ago was much warmer than anything we've seen or currently seen. It was about up to at the very peak, we believe, from these records. You see the black line here. That's our records of temperature. It's sort of 16 degrees warmer than the sort of the period in the middle of the 20th century, which is, warmer than anything that we've seen, and actually is warmer. However, these changes were occurring on time millions of years. The temperature may have gone from being 8 degrees warmer 58 million years ago to 16 degrees warmer 50 million years ago, but that change occurred over 8 million years. And it's very, very different to changing global climate 2, 3, 4 degrees over the matter of a couple of hundred years. And it's often that rate of change that is the difference between what we see in our current climate change and what we've seen in past climate change. But how do we know how this climate's changed? Well, depending on how far back you go, we quite often have to use proxies. So in the study of past climate, we use a range of proxies. And this is basically anything whereby it's not a thermometer. So there are a range of different ways. Most famous, of course, is probably ice core drilling. I'm certain most people have heard of ice core drilling. You drill down into the ice cores, you can extract the air from the bubbles frozen inside the ice, as sort of highlighted in this image in the right-hand side, and measure various compositions of gases to get an understanding of both the atmospheric makeup at that time, but also to do an analysis on the isotopes of the water in the ice, which tells us sort of roughly how much ice there was, and therefore you can calculate an estimate of global temperature. The same techniques can actually be taken further back in time through ocean core drilling. So we've got a drill ship here in the left-hand side. That's the JOIDES resolution. It's part of the Integrated Ocean Drilling Program, or the IODP, and they sail around the ocean drilling holes in the seabed to extract cores of mud and sediment. These generally go back about to that sort of 65, 70 million period, depending where you are in the world. And a range of different techniques can be applied. Some of them are chemical-based analyses, and some of them actually go to sort of identifying individual species. So what we have here, as you see, this sort of lovely ghostly image, is a scanning electron microscope image of some fossilized plankton. And you can either measure the chemicals in the shell of the plankton, or you can actually identify the species, which is actually the picture here. This is a former colleague of mine, Lindsay Fox. And Lindsay's PhD was all about identifying these microfossils for a particular period of time. And once you find clusters of these microfossils in certain cores, you can actually generate an estimate on the temperature, because you have an understanding of their modern equivalents, where they live, and therefore how these ones would have lived, and alongside other sort of records of temperature things, allows you to build up this like nice picture of global temperature change. And around the world, we use a range of these different methods, which allow us to take these records back sort of 65 million years. Other records that we use, similar to the ice cores, but shorter in duration again, we have speleotherms, or sort of as they're also known, sort of stalactites and stalagmites. They grow at a particular phase, and they grow in a layers. You can see they've been cut in half here, and again you can measure the layers and get an understanding of the different chemical compositions at different times, because they're created by water flow. And also tree rings, which is again probably one of the other more famous records. And again, in that sort of shorter time period, if you've got a dating on the tree and how old the tree is, you can create a climate record by counting the rings and by analyzing the rings. And again, a range of techniques, from sort of understanding the tree's biology, but also through using chemical analysis. So we have a really detailed range of ways of understanding how our climate has changed in the past, and there's also supporting elements of geology, looking at how the rock record tells us how the location of the continents has shifted over that period of time, and that allows us to build an understanding of the flow of ocean currents, the height of mountains, changing airflow, and all these sorts of things. Allows us to build this picture, as in that image I first showed. Depending on what you pick, you can go to the sort of the 1650s for the Central England temperature, or sort of the 1780s for a pan-European record. But as we got more recently, the last couple of 100 years, we actually started to make observational records of the climates, whether this was enthusiasts taking measurements in their own sort of gardens, just how the Central England temperature record and started, or actual sort of formal organized Met agencies starting to do analysis of the weather, or just the sort of the analysis that was done by ship logs. So I'm sure you've come across projects such as Old Weather, where they have gone through and they're scanning and then documenting the records kept by ships, where they measure temperature and pressure and wind speed as they were crossing various oceans. And obviously these records are dated, so it allows us to build up these ideas of how our climate existed in the past. Now, on land, we used fixed thermometers, weather stations. You can see an image of one in the left. And, we have at the Met Office, we run the WOW network, which utilizes personal weather stations. But again, as a good example, as I've already talked about, the distribution of weather stations and things like that can be very biased depending on where you are in the world. And you can see that the WOW network has got wonderful coverage in the eastern United States, Western Europe, and Australia, but a very poor coverage across much of the rest of Eurasia, China, or even sort of Canada and Africa. So these networks aren't always perfect, and these sort of periods of times in the past, again, we've had areas where ships travel frequently. We have very good records, but there's also areas where ships avoided because those weren't convenient passages, or they weren't considered safe regions. So there's no record. So these sorts of things have an issue. That's obviously land records. At sea, we've used buckets, and one of the biggest challenges in understanding observed climate, and I talked about in the first video about how we've had to adjust records. Well, one of the adjustments that has to be made is whether or not the bucket used by a ship was made of wood or made as a leather bag. And this had an impact on actually how the water cooled as it was being lifted up to the ship out of the sea. And it's those sorts of details. Modern day, of course, we use these buoys that basically create weather stations at sea, and they're tethered and floating, particularly on sort of continental shelf regions. But as I've said, we still have regions where we don't have a lot of data. And that's where perhaps in the last 40, 50 years or so, we've had the real benefit of the satellite era. Satellites are fantastic because they provide coverage of data poor regions, so Africa, Antarctica, and the Arctic. where there aren't a lot of people, and maintaining weather stations that are working is immensely difficult. They're not perfect. They still need ground validation. You've got to be very careful about how you actually work with the data, but they still provide us with a wonderful wealth of information that we just wouldn't have, particularly if things such as sea ice extent and the growth of winter sea ice in particular, at both the north and south poles. Similarly, even commercial aircraft provide vital sources of data, much as in our sort of, the era of Victorian and early 20th century shipping measurements. Well, planes are constantly measuring the conditions as they're flying. And actually, one of our challenges, weather forecasting during the COVID pandemic, was the period of time when international aviation was essentially grounded, and that we lost a vital source of data for our weather forecasts, and we had to learn to adjust to produce weather forecasts without that source of information. So how do we study the climate into the future? Well, that's where we use a climate model projection. Now, climate models take this. This is the Earth's climate system. It starts with the sun, and the energy from the sun drives everything. That energy interacts with the Earth's surface, with the land, the ocean, the sea ice, the ice sheets, the clouds, and the atmosphere. We have volcanoes. We have human contributions such through greenhouse gases or changes in land use. Whether there's a forest or whether there's grassland affects the local climate, and the way the wind interacts with mountains, and that creates areas where on the western side of, particularly somewhere like the United Kingdom, the western side of the UK is traditionally predominantly wetter than the eastern side. So somewhere like Cambridge in East Anglia will only get sort of about 480, 500 millimeters of rain per year, whereas here in Exeter we'll get closer to 1500. So you get a real difference depending on where you are, west versus east, for example, because of the way the flows of wind and the way they interact, whether that wind is coming off the ocean, whether that wind is coming off the land, and all these things come together, and that is what makes the Earth's climate system. The climate models take all that information and they turn it into mathematical equations. Now, I'm not going to show any more equations, I promise. That and these are just some example equations, but we take everything we've got and we turn it into maths. And from that maths, we are able to spit out a climate model projection. We're able to say to the climate model, a computer program, here is our system, here is what we expect to happen in terms of the change in greenhouse gases. What do you think will happen in the future? And you can see here we've got on the left a low emission scenario, on the right a high emission scenario, and we've got end of the 21st century climate projections. And you can see that it's much warmer in a higher emission scenario and not as much warming in the lower emission scenario. And on the bottom, we've got the changes we expect in precipitation. So what is a climate model? Well, it's a tool. It's a computer program, but also it's our only way to project the future, and it's a way to interrogate the past. So as well as the past climate records that I've talked about being produced by actually analysing fossil plankton, ice cores and things like that, we can actually then set our climate models to try and work with this data to understand what happened in the past, the way the climate system worked then, and see if any of the lessons we can learn from the past can help us understand the future. They allow us also as a tool to investigate what would happen if we changed little things, and to do to investigate what drives the climate system and what drives different mechanisms. You can swap out. For example, I've done work in the past where I provided the climate model with the sea surface temperature and the sea ice conditions, and I gave the model a situation where it had high sea ice cover and the warmer sea surface temperatures together to investigate what happened to the interaction, to get an understanding of the strength of that interaction where the sea ice meets the warmer ocean, what happens in the atmosphere. It wasn't something that ever happened in the real world, but it allows us to understand processes that are happening in the real world. So that's, again, climate models allow us to do these things. Now, computers are ever improving, and this has been really important for a range of sectors. Apologies, particularly those that rely on our weather forecasting capability. But it's also played a massive role in how our climate models have grown, how our models have changed. There are two elements of this where it's particularly important. Firstly, how our models have increased the number of processes that are, as we say, interactive, or how they look at things interactively. This is when the processes actually react to other processes within the model. So we've got this little figure on the left, and we've got, starting at the mid-1970s in the top left, you can see that basically a climate model had some CO2, the sun, and rain, and nothing else. And then we started to give it a land surface, give it some ice, and give it clouds. And then suddenly we were able to add in an ocean. It was very, very thin. It was like saying the entire global ocean was about 3 meters thick, but it was some sort of ocean. And then we were able to start bringing in a deeper ocean as we got into the mid-90s. We started to actually say, well, actually, there's volcanoes. And actually, there's some chemicals that come out of factories. And then as we went on, we were able to tell our ocean that actually the ocean has processes that cause it to create circulation, the thermohaline circulation, or the Gulf Stream, as you might have heard it termed. And we're able to include that. And then we're able to and we've been constantly able to add in more and more elements because computer power has increased and has allowed us to make these models more complex. Secondly, we've been able to make our models more detailed, by which I mean we talk about a term called resolution. And it's called resolution because it's how we resolve our models. The smaller the area of our model, the more detailed it is. So this little figure on the left shows you Greenland, Iceland, and Scandinavia and Western Europe through 4 different iterations of the Intergovernmental Panel on Climate Change reports. And you could see in the top one, when climate models had a resolution of 500 kilometers. So that means that each side of the box that we're drawing was 500 kilometers. So a grid square was 500 square kilometers. You can see in that top corner, the UK doesn't exist because the model wouldn't see it. It doesn't exist because it's smaller than the area of the grid box. So it's removed. You can see once we got that down to 250 kilometers that we sort of exist. And Iceland's also appeared, so good for Iceland as well. And as you go on, you can start to actually see in that the third image, you can start to see there's actually you can see that there's the island of Ireland, and there's Great Britain. And then as time has gone on, these models have got more and more detailed. And this is I give you an idea of where we're at now with the UK climate projections. We have a global model at 60 kilometers scale, and if you sort of squint a little bit, you can believe that's the British Isles. We have a regional model that covers the area that sort of is the start of your weather map. So from Iceland in the top left-hand corner and Italy in the bottom right-hand corner, that sort of area, that's at 12 kilometers scale. And you can see that is definitely the British Isles, and you can even see that there's some mountains. You can see the Highlands of Scotland. You see the Welsh Mountains, and the Outer Hebrides has also appeared on this figure. And then we also have a British Isles domain model at 2.2 kilometers, and you can see there that we start to really resolve the detail. I always like to point out at this stage, actually, we've gone from seeing that the Welsh have mountains to the Welsh have the valleys that they're very passionate about. And you can really see the differences that exist around sort of coastal regions. So this allows us to get a much better idea of the climate system and how climate change is impacting on the UK. Now, that does come at a cost, and that cost is particularly storage. So this global model, we have 28 different versions of the simulations covering 200 years, and it takes up about 130, it takes about 0.13 terabytes of space. That continental model, we've got half the amount of time. We've got a little less than half the ensemble members. It's now 4.2 terabytes. When we go to our national scale model, currently 60 years of data, it's 23 terabytes. It's huge. Now, this most recent CMIP6 report, actually, the CMIP6 data contains 100 petabytes of climate model information. It's a staggeringly large amount of information. So actually, climate change and climate modeling now requires both supercomputers and huge amounts of cloud storage, so we can store the data and share it with people, allow people to work with it. So that's what a climate model is. And individually, you can use a single model to investigate features and details. Climate models are best when they're actually brought together and put together in these big cohorts of climate models. You can then start to see the range of futures, both that in a general trend, but also the uncertainty and that range of uncertainty that we might have, because no one model is ever going to be correct, but together they sort of produce a good broad understanding of that future change. So that's taken me to this point, and I'll pause here and we'll and hopefully I'll see you again in another video.